Thank you. Okay, cheers everybody before we get into this. SPI subsystem. My name's Matt Porter, as he said, and let's jump into it. So, oops. Of course, now it quits working. How about that, huh? Well, it worked just a second ago. All right.
Next time you throw it.
Exactly. All right. We'll do it manually. All right. All right, just to de-obfuscate the name of the thing, our community has gotten more diverse, so people might not get Heinlein references. So we're going to understand intuitively the SPI subsystem, hopefully, by the time we get done with this. So if you haven't read it, read Stranger in a Strange Land. Awesome book. All right, little overview. We'll talk about what SPI is, okay? We'll go over some SPI fundamentals because we can't truly understand the subsystem unless we really understand how SPI works first. So we've got to go through that first. We'll talk about some fundamental Linux SPI concepts, so how the subsystem takes the concepts of SPI itself, translated in the Linux world. And we'll look at some use cases to kind of drive us through the subsystem, right? Adding a device, doing a protocol driver. We'll talk about what that is, how that relates to the real world of SPI, controller drivers, user space drivers. And then we'll talk a little bit about performance and then what's coming up in the future. All right, so getting into what SPI is. So serial peripheral interface. Motorola developed this. It's a de facto standard. So if you're hoping for a written spec with a committee, you won't find it here. It's a master-slave bus, 4 wires. And we'll talk a little bit about the signals coming up here, except when it's not. So 4-wire sounds like the easy case. Everybody talks about the standard case, but there's a few others. We'll get into those a little bit. Options where you don't need to use all the wires and so forth, or use more. So there's no maximum clock speed. Obviously, there's practical limits that chips run into. But then this really poorly formatted URL is obviously the usual place you can go get some information on it. So if I lie about anything, you can go there and find the truth, hopefully. So, and one of the jokes about SPI is that everybody makes a big deal about it, but at the end of the day, it's just a glorified shift register. All right, so what are some common uses? Where do we see SPI used? Well, pretty much everywhere, but just to highlight a few of them, you have things like flash memory. You guys often find serial flash devices. Why do we do that? Why do people design those in that way? Low pin count, right? Same reason you see I2C EEPROMs, right, for your non-volatile storage. Huge advantage with that low pin count in embedded systems. So again, same reasons drive its use with analog digital converters. A number of different sensors. Thermocouples, for example, you might say, well, that's just a temperature sensor. I know that there's lots of I2C ones and they're low speed, right? But in industrial use and so forth, things like thermocouples have to be sampled at very, very high rates of speed, right, in a process control that has very little deviation permitted in the temperature. LCD controllers, you start seeing a theme here, right? And of course, as we saw this morning, the Chromium embedded controllers can use SPI as one of the communication channels. One of the themes here, when we look at all of these, okay, is that they're all fairly high-speed type devices, right? ADCs, thermocouples in the kind of sense I gave, where it would be sampled very quickly. LCD controllers can have a very high rate of speed if they're a color controller and so forth. All right, so now that we've got that little overview out of the way, let's hit our fundamentals. So we start with our standard signals. And here it can get a little bit ugly when you're looking at data sheets, and we're going to talk a little bit about data sheets and translating those into some reality of extracting the information you need out of them. But you start with MOSI, as I pronounce it, master out, slave in. And what I show here is you're going to find a lot of different names for this. Because it's a de facto standard, every manufacturer, vendor seems to have picked some different things. And I've even seen data sheets where they'll show I2C names, right, for the data in a half duplex type device. So that's why SDA is on there as well. So you'll see all these. It depends on the vendor. Same thing with master input, slave output. You'll see that same set of things. And then your serial clock, okay, that's an output from the master. You'll see those kind of different monikers for it. And then you have the concept of a slave select. That is a master output. And so that's how a SPI device is actually selected, should there be more than one on the bus. Okay, so clock, you have output and input, okay? And so that's the 4 wires we talked about. That's our common case, right? And keep in mind, as you see this, that if we've got a dedicated channel for output and a dedicated channel for input, it's a full duplex protocol by its very nature. So this is what it looks like in our really, really trivial example, right? So we got our SPI master, we got our flows for each of those, and if you want to do a transaction, he would go ahead and assert this slave select low, right? And say he wants to do a write, he would put data on there and clock that, okay? Now, we're going to look in detail how that works, because you can't verbally explain it and give it justice. So let's look at some timing, okay? And with these wonderful timing diagrams that Wave DROM helped me do, we'll look at, and don't worry about write mode 0 yet. We'll explain modes, okay? But we have a typical write cycle in 0. And so what you're seeing here is just an 8-bit transfer, okay? And in this case, what is usually the de facto standard is MSB first on the wire. So that's why you're seeing D7 down here. And so what you see is you see the data stable here. Boy, I can't really hold this. I must be nervous, huh? Yeah.
No, it's just hard.
Yeah. Thank you for that. So as you'll see, it's latching that data on the rising edge is what we're showing there in a write, okay? And you see it on the master out, slave input. Makes it easy with the name if you use those signals to know which direction you're going there. And then on the read case, okay, you have it latching on the rising edge here. And you can see that this chip select went low, right, before that first edge for that bit, all right? So that's your very basic case, all right? We'll get to the modes here in a second. And here we are. So SPI modes, you have lots of options. So there are many modes, but it's a pretty simple truth table. The way it breaks down is you compose it of 2 characteristics of your clocking, all right, relative to the data, all right. So you will see CPOL is the abbreviation you'll typically see for clock polarity in most data sheets and in the original SPI description from Motorola, and then C phase, the clock phase. And so right here we see how those break down. So if the polarity is 0 or C-pole is 0, then your idle state of your clock is low, right? And so it's transitioning from low to high in the active state, all right? And then the inverse is true if C-pole is 1. So that allows options on the clock polarity for devices. And then in the phase, very simple. Some people forget it, but your data is latched on falling if C phase is 0, okay, and then its output on rising, and then on 1, it's latched on rising. So this is going to vary on the type of peripherals you deal with and so forth. So you end up having to program your controller to operate with the proper phase for whatever peripheral you want to talk to. And so what they've come up with is a way to encode these that's a de facto standard as well, that's simply modes 0 through 3. So if you're used to seeing modes 0 through 3, that's how they translate back, all right? It's simply just telling you what polarity of the clock and what phase I'm latching data on, okay? All right, so now let's look at these modes, right? I showed you the basic example. It was writing and reading in mode 0, okay? So now let's look at each of them individually. We'll just look at writes, just because it doesn't matter for illustration of this concept, okay? So what you see first, right, is our chip select's going low, all right, to activate the chip, right, at this edge here. Don't care what the data looks like here, all right? And then I have my first clock edge, and so this is just like, this is the original example we looked at, okay? And so you see it's latching data on each rising edge, and notice that it was idle low, right, clock. So that would be the clock polarity 0, right? And then the phase, right, rising is where it's latching. So then we still have clock idle low in mode 1. If you remember our truth table there, whoops. So when we're looking at 1, we're just changing the phase, right? And so now you see that instead of latching on the rising edge, it's latching on this falling edge here each time. You see how that lines up with each stabilized data bit, okay? And then when we go to write mode 2, all right, now C-pole is 1, right? So our clock is idle high. So that's why you see this waveform. It's high, and now we're going to a falling edge, okay? And in this case, I show falling edge, right? Falling edge latched there. Remember, they're all right, so that's why it was Mosey. And down the line. Same thing here, except in mode 3, it's on rising edge, right? So that's all the modes, okay? All right, so, but we only looked at this really trivial example, right? Single slave and so forth. Now it gets complicated because we live in the real world. So first off, obviously, we've got the reason we have the chip select in the first place was so we can have multiple slaves on a bus. And the way to think about a chip select is, from a software stance, that gives us an address, right? So everything has got to have a unique chip select in order to activate the chip, activate its buffers, and so that becomes a convenient abstract way to reference multiple slaves connected to one master. Okay. The next thing that get complicated is daisy chaining, and the very common case that they'll show with daisy chaining is the daisy chaining of the MOSI to MISO on each device. But there's also daisy chaining cases. In fact, the Anodyne analog field program analog arrays, they do chip select chaining during configuration. So they shift so many bits, and then it asserts another chip select. So now you don't have the master controlling the chip select down the line, and so that can get ugly as well. Okay, and the next area, I promised you there's lots of ways you can abuse the fact that it's a 4-wire bus. Well, in high-speed flash devices, they started adding more lanes, right? More lanes, more throughput, right? So there's a balance there on pin count versus your ability to burst read data off your SPI flash. And we'll see that there's devices that, SPI flash devices that do dual or quad. Quad's popular. So essentially, instead of one MISO, we have N number of them, right? And there's nothing preventing, I can't remember if there's some eight lane yet, but it probably goes beyond the point of doing it. And I know that the quad ones are very close to or right around the parallel NOR flash speed now anyway. So obviously, like I said, that increases your throughput. So every time you add another lane like that. All right, and then the last one here, variant, is the 3-wire variant, microwire. And so what they do is they combine MISO and MOSI, and it operates in half duplex. You can also do things like say that your peripheral is a write-only peripheral, right? Some LCD controllers, that's all they are, right? And you don't even need MISO hooked up for those if you're just caching the contents of the registers and operating from reset. So a lot of designers just won't hook up a pin if they don't need to read back from it. So essentially you're back to a 3-wire bus. Or maybe it's your only device and you drop the chip select and it's always asserted. So there are designs like that as well. All right, so looking at that more complex case, which is really the more common one that you'll run into, what you see is the same type of flow, okay? And MOSI, MISO, and the clock are all propagated to all 3 of these together, right? But you'll see that each one of them has a unique slave select now, or chip select, right? SS1, 2, and 3. And if you can read this eye chart, so it's hard to fit this stuff on there. So what you see here is this one here, and I know that's probably hard to see. I knew this one was going to be tough, but that's slave select 1, 2, and 3. And so this is just showing, 3 8-bit writes, okay, each to each of those slaves. And so when you see the timing of that, how you manage that is you drop the chip select for SS1. This is write mode 0. And so what you're seeing is when that chip select is asserted, you see it latching the data for the first slave. And then you see slave select 2, right? You see that unasserted, that go low, and now slave select 2 is receiving 8 bits of data, and the same thing. So that just shows you what it would look like if you were dumping that on your logic analyzer. Okay, we're through that background now, right? So now that we understand those concepts, now we can talk a little bit about the Linux SPI subsystem. So now every subsystem, the kernel has to translate this hardware into some sort of concepts that we can use. And of course, with the device model in the kernel, the way it's broken out in the SPI subsystem is we have a concept of controller and protocol drivers, okay? And those match up one-to-one with what the controller is, that master that we saw, and the protocol driver is whatever protocols needed on top of just shifting bytes out to actually do something with your peripheral, okay? So as I said, the controller drivers, that supports the SPI master controller. Both of these run on your SoC, if you will, okay? And all the controller driver does, right, the subsystem is very carefully split out that protocol of the peripheral from the actual shifting of bits out of that controller and so forth. So all it's doing is controlling when that clock comes on, when the chip selects are asserted, or slave select, if you will, shifting the bits, and then configuring those characteristics so that you get the right mode, you get the right frequency of a clock, and so forth, okay? And of course, the polarity and phase, right, as we showed encoded in the modes, all right? So an example would be like for Raspberry Pi 2.3, the 2835 driver. So now protocol drivers, as we said, very carefully split that concept away. So you don't, if you're writing a protocol driver, you don't have to think about what controller am I on, what are its characteristics, to a point, right? That's all abstracted for you. So the way to think about them is that's your slave-specific functionality. So if I've got an ADC, it talks to whatever that ADC says for, these are my registers, this is how I get samples started, and this is how I read them out. That's what you're coding up in a protocol driver. All right, and so fundamentally, every operation in the SPI subsystem is based on top of the concept of messages and transfers, okay? And we'll talk about those in detail here and really understand that as it relates to the APIs. But that's a fundamental concept they've added that's somewhat, outside the realm of that low-level SPI hardware, but maps well to how peripherals actually use SPI in functionality. So remember, the protocol driver relies on you having a controller driver. It doesn't care what controller driver, everything's abstracted for you. So an example would be like one of these old MCP 3008 ADCs. So as promised, so communication, the subsystem, of course, it breaks everything up into transfers and messages, okay? And so a transfer, and if you think back to those timing diagrams I'm showing, right, a transfer, if say my device wants an 8-bit, has 8-bit registers that it implements behind it, okay? A transfer might be a single 8-bit read or a single 8-bit write, okay? In generic terms, it's a single operation between the master and slave, okay? Part of the transfer data structures, what's carried in there, remember, it's a full duplex wire protocol at the low level. So each transfer structure carries both TX and RX buffer pointers. So, one can be consumed and the other filled, right, within the same operation. You can make either null if you're just doing a half duplex operation, okay? And each transfer can have its own optional parameters set on it. So you can control what happens with the chip select after that operation ends. Okay, and that matters a lot when you go look at your peripheral data sheet. It may say, oh, you can't drop the chip select after a certain sequence of things. So you can go per transfer define how that's going to behave, and then you also may need to insert some delays in there to satisfy the timing, and so there's ability to do that. Okay, now that said, what are messages? Just an atomic sequence of transfers. So when you build up a message, you can add n transfers, all of which can have this individual behavior of how they manage a chip select, a delay in between, and so you can build up that message for whatever your peripheral data sheet says. You need this sequence, right? You can build that all up, add the delays and so forth, okay? And so the message itself is the fundamental argument to all the SPI subsystem transfer calls, the read-write APIs. And there's a bunch, and we'll talk about that. But just to give you an idea, if it wasn't clear verbally, that's the best way to kind of look at a SPI message, right? You got a chain of transfers inside of it, n number of those, pretty simple. All right, so let's use some use cases to walk ourselves through the subsystem now. So I want to hook up a SPI device, right? I know there's a kernel driver for it, like let's say the MCP32OX that runs the MPC 3008. But how do I hook the damn thing up and get it working on my board, right? So the next one, I want to write a protocol driver, I want to write a controller driver, right? Or I want to write a user space driver because I've got something odd, or I want to do something different than a kernel driver for some reason, or I'm lazy. All right, so adding a SPI device to the system. The first thing is you need to know the characteristics of your device. You need to understand the timing of it in order to properly add it in, because you're going to have to set some parameters, okay? So learn how to read a data sheet if you're going to do that. Even if you're using an off-the-shelf one, if you don't understand what the max frequency is, then you're not going to be able to hook it up right, okay? So there's 3 methods to do this. Device tree, obviously pretty ubiquitous. So we have it everywhere now. The board file method that's basically deprecated now, except x86 people tend to use it sometimes. And then ACPI, which a lot of drivers are getting ACPI ID tables now to support that. All right. Wow. So learning to read data sheets, right, for SPI, there's a few important things. First off, you might not even notice when you look at the data sheet. Sometimes they don't even say SPI, right? And they'll just say, it's got a serial interface, and you have to kind of go look at it, and maybe they're masking because they don't want to say the Philips I2C name or something, right? So it might be I2C, but you got to look a little bit. Usually they'll say, this is a SPI device. So there's a few clippings out of an ST7735 LCD controller. And what's important, this was one of those examples where I was not kidding you. They show SCL and SDA, but it's SPI, right, when they show that timing, okay? So, and that's also an example of one where I said, if you're write only like this, since I know this part well, you have a situation where it's essentially a 3-wire setup. There's no need to have the read path. It's optional. So they actually show a 4-wire hookup as well if you do want to read certain status things, but most designs don't even hook that up. So important things here. Identify at the beginning it's a SPI device. Okay, that's pretty obvious. But then, be aware of your timing diagram. You have to be able to read the timing diagrams. They're not much different than the stuff I drew up. They got a lot more detail though, right? So if you're a software person that hasn't got comfortable with data sheets, now's the time to do so if you want to do something with hardware. So you need to look at things like this time here, right, which is the time between where you drop the chip select, right, or you insert it, and when that first clock edge starts, right? And then they're showing things like the period by this high time and low time, right? So now you have the period and thus the frequency. So if you can do simple math, you can figure out what's your maximum frequency. So that's generally how they communicate that information to you. So yeah, and so you'll see, they've got that setup time, right? And they've got hold times and so forth. And so that's where you get your frequency from. Just a little bit more on that. And then what happens is all they were doing in that timing diagram is showing you a very low level, right? So then later you're going to see more information that's actually how their protocol works. So in this part, it's got the concept of a data or command type state. And so you'll find tables like this where now you're talking protocol, okay? Now it's showing me how, in this case, on the data line, this is a data or command flag. And so everything that's following in that 8 bits, okay, is everything following that then is either a command, which could be a register access, right? Or if you're doing data, you may be just streaming your frame buffer, right? If you're using the FBTFT stuff or the new DRM stuff they're working on for that. This is where you start seeing that. So you need to look for how those registers are mapped and so forth, and that's where you get what you need to do the actual protocol driver, the guts of it. All right, so let's look at another example real quick. That's one where it's a LCD controller. I'm going to use this example when we go through hooking things up a little bit. Again, it tells you, it says, I'm a SPI device. Somewhere at the beginning of the document, these are just clippings I snapshotted out. Again, same type of timing, okay? And they show T high and T low here. Add them together to get your period, and you find out that it can do a max of 4 megahertz. Well, nominally, people find that everything works out of spec, but in reality, that's your safe time. So same thing there. And again, just reiterating that it's one thing to have that low-level timing. It's another to go further in the data sheet and you start seeing how the AD converter goes, right? When it starts doing its conversion, how soon after that the data is available. And D out here, if you remember, they use, back to, I described the signals and all the different names. That's the MISO, right? That's master in, slave out. So
half duplex, you mean?
no, this is a 4-wire. It's just using the alternative naming for the things, so just don't get confused by that. If you don't see MOSI and MISO on the data sheet, D out is also MISO. Right, that was back on that earlier slide on the signals, all the different crazy names that we see used. Oh, this turned out terrible, huh? Contrast is not good, huh? Well, can you guys read that at all?
Not really good.
Yeah, you guys can.
Turn the lights off.
Yeah, can we turn more of the lights off? Because I think it'll be legible enough. Otherwise, I don't have any examples.
One more.
All right. Thank you. Now this is an intimate setting, right? Okay, so this is not Groking DT, so I expect you to know it, but this is just remember where to reference and find information for SPI stuff. You go, if you're going to hook things up, so we're back to let's hook this thing up, right? Via DT, go look at the binding, right? Documentation, device tree bindings, right? And sure enough, we find this, and I clipped a little bit out of this for the example, but one of the compatible strings is microchip MCP3008. There's some deprecated ones in there as well, and then there's a little example of how you would hook it up there. That's for a 3002. We have a 3008. And so let's say, again, I'm not showing every variant of how you can actually implement this, but just as an example, a DTS fragment for this device would look something like this. If you don't understand DTS fragments or DT fragments and overlays, that's a different talk. But the important thing here is that in the overlay, the operative piece here is that this reg here is a chip select or your slave select. So that's your unique ID. So you can use it like an address, and that's how the subsystem uses it. Okay, you got that compatible string that we saw in the binding on the previous slide, and then we figured out what our max frequency was from our data sheet because we're smart, and we're going to plug it in there. Okay, so 4 megahertz there. Now, this is how you do it the wrong way. So if you've got a board filer, you're on something like maybe a Minnow board, right? Typical developer board where you don't have DT handy and ACPI doing overrides is really a pain. You do this type of thing, which is well documented in the subsystem docs. This is the old way. So normally you'd see in a board port, you also see this structure and so forth. In the old days, before DT, you'd see all the board files in the kernel registering all their devices this way, right? Just in a big array here. So this is just an example of one. Again, same data that we needed, right? We know we're bus number 1, chip select 0, and this 4 megahertz rate. And we also need to tell it what module. Doing it by ACPI is almost unreadable, as with most ACPI stuff. But you see there, basically the same things are there. It mixes a bit up here. You've got the clock polarity and so forth. You've got the max frequency. That's this one here. So that's your 4 megahertz. In machine readable form. So that's what that looks like. So 3 ways to get there. It just depends on your platform, right? So you'll see these type of constructs on Bay Trail type. If you dump their ACPI, you'll see some of the stuff for SPI devices. It looks mysteriously like that. All right. So that's how we hook one up. Basic example. Time check. All right, we're good. So now let's talk about protocol drivers, okay? And now we're getting into the meat of things. We're going to come back to the whole messages and transfers and so forth, because we're now going to use some of that as we get into these. So if I do a protocol driver, standard Linux driver model, okay? You find these same patterns throughout the kernel. So you have to instantiate a struct SPI driver, okay? And so there's a few important fields, okay? Once the probe fires, so again, we assume that you know the driver model, first off. We're not going to cover all that here, but just as a highlight of what you've got to fill out to do your protocol driver, okay? You have your optional PM ops that you probably want, and you got to probe and remove, which all standard hooks you're going to find in everything that works in the driver model. The important thing operationally with a SPI protocol driver is that as soon as it probes, you can start using the kernel APIs to do messages. Okay, so that's immediate, and so once you implement that probe, you can start banging on the device using the in-kernel APIs. So what are these APIs? These are the APIs you're going to use to build a protocol driver, right? We said the subsystem's carefully architected to separate out that controller thing. So all we have available to us are these neat little transfer APIs. So the first is SPI async, and it's not really an obfuscated name. It means what it says, right? So that's an asynchronous message request, okay? And when that message completes, you get a callback executed, all right? The key with async and when you're using these is that it can be issued in any context. And we'll explain what the other side of that is in a moment, but you can execute that, for example, in IRQ context, since it does not sleep, okay? Now, SPI sync, and I will say that when you look at the type of drivers that use SPI async, you find it's not heavily used directly, okay? And we'll get back to that in a second, but so now let's talk about SPI sync, okay? Again, synchronous message request, right? It does exactly what it says. One thing implementation note is that everything, all of these synchronous family calls are all wrapped around SPI async, right? So the same backend's used, but they guarantee that it will return on completion. So you can only issue this in a context that can sleep, right? So if you need to be in an IRQ context, you're going to have to use this guy, okay? And as I already said, it's a wrapper around those. And so you can build up complex messages and then issue them with the SPI sync, okay? And then there's some helper calls where you can just hand a buffer and do a write and a read. And so those are just wrapped around there. What you'll find is you'll see things like some of the network drivers will use SPI async. They're more optimized around throughput, and so they can drive everything off of callbacks that way. Things that want low latency, right, are going to want to use something based off of SPI sync. They may have a short little command to send, and they don't want to have some arbitrary amount of time and handle the callback coming back. They want to do it sequentially. Then you have some specialized APIs. Well, just this first one. This is kind of out of order, fortunately. So SPI read flash, you've got an API. If you deal with SPI flash devices, they have a standardized set of commands, okay? And so that's actually optimized for that set of commands. It's also optimized around specialized engines, like some of the quad SPI controllers on the newer SoCs. They'll IPL out of that quad SPI flash, and so they have memory mapped I/O, and it actually triggers SPI transactions on the bus by accessing that. So they'll demand page in chunks of the SPI. Of that SPI flash device into that MMIO area and execute the code XIP there. So that supports those types of things. And then when you do need to build up the message, right? We show how you have all these transfers. There's APIs to do that, and so not surprisingly, you can SPI message init, and that initializes the empty message, right? So you're dealing with that kernel structure. And then you can SPI message add tail and just add transfers onto that list that we saw in that diagram earlier. So you can put any arbitrary type of transfers together, different characteristics, how they leave their chip select, everything by using that API there. All right. That covers APIs that you're going to use with protocol drivers. With a controller driver, again, standard driver model. Not everybody's going to be writing one of these every day, right? Usually you're going to be touching protocol drivers for most people. But it works, again, like a lot of other subsystems, right? We have those strong concepts of master, right? A master device, and also called a controller in the subsystem. And so you're going to SPI alloc master, and then once you've done that, you need to set a whole bunch of methods, right? And so set up, configure SPI parameters, cleanup, prepares you for removing the driver, and then you have four different that are the meat of it, right? And so one is prepare transfer hardware. So you have to implement, you may need to do some preparation for a message is going. So when the message pump in the core SPI subsystem is about to send you a message to be processed by your driver, he'll let you know before he calls transfer one message, or before, so that you can get ready so you can call transfer one message. So you get a hint there that a message is going to arrive into your driver, okay? And transfer one message does exactly what it says. You dispatch a message there, so when you get called by that. And then transfer one is just dispatch a transfer, all right? So you implement all those, and then you register it with the subsystem SPI register master. Okay. Okay, so user space drivers. Obviously, this is a popular one with all the developer type boards, and the maker community likes to do the user space type drivers and wiring Pi and stuff like that over top of things. The way that's done is through a protocol driver, a special one called SPI.dev, right, that exposes a simple character device out to user space. Okay, so when you bind that SPI.dev driver to an actual device using methods that we showed earlier, okay, you get these instantiated. So you have SPI.dev and whatever your bus dot your chip select. So that gives you that unique address per bus, remember? And so same thing, you'll see information on it under sysfs, and then you see that character device there. And usage of it is very straightforward. So simple open close. You've got half duplex read and write commands just by their nature using the standard calls. And then if you want to do more complex things, yes?
So half duplex in user space, I didn't realize that, but what actually happens in that case to the actual transfer, does it just get discarded like the other half?
So if you look at the actual transfer struct, when you're just doing a write, by being half duplex, that just means that you can't set up a full duplex transfer using that API.
On an SPI level, it's always full duplex.
Yep.
Does the other end just get thrown away?
Yeah. So that would be the case. You would do this very commonly, even in kernel space, where you just say you want to do a write, you would set the RX buffer to null, right? So that's a common pattern if you were building it up, by scratch. And so that's what happens underneath those types of calls, right? Good question. So to get more complicated, SPI.dev does support very complex drivers. So to get at that, you have to go beyond read-write that aren't sufficient and use your I/O controls. And so there's a few, don't show all of them here, but the important thing is, and you can read the docs on it yourself, but the important thing you've got there is the SPI IOC message. You can do raw messages, full duplex, you can control the chip select, everything, and then you have a whole family of read-write IOCs where you can set all the same SPI parameters that you would in the kernel APIs. So you have full control. You can build up complex messages with lots of different transfers, just like you can in kernel space. Best place to go to get more details on that is in that SPI.dev doc, okay? And then what's great is the kernel has, and sometimes people aren't aware, in the tools directory, a couple great examples. So you want to see that thing used, in a raw way. There's a full duplex example. There's a test piece that a lot of people use in their examples. And then once you move beyond that, I can recommend Jack Mitchell's libsoc library has a higher level. It fits into his whole libsoc API, so you have a uniform API, makes it easier to work with SPI.dev. Maybe a lot of times you want to use GPIO too if you're doing user space stuff, so you have a common API. So that's helpful. It's a very, very familiar standard C library. And then a lot of people, I think Leon and Avi was talking about, Python and stuff, and the maker community in his talk, and a lot of people are using this Python binding to SPI.dev. All right. All right, we're almost there. We'll talk a little bit about performance. So this is all well and good. You got all this abstraction. You've got these standard APIs and everything. But at the end of the day, you need to understand how to use them properly, right? And so first thing that happens when you have bad performance is you probably missed some characteristic of the controller driver. So we got all this nice separation, but there's always going to be some things that aren't fully abstracted, right? And you find one of those where down in the controller driver, the McSPI driver on OMAP that's used on pretty much all the TI parts, right? They actually they have hard-coded, because of DMA overhead, it doesn't use DMA until you get beyond the 160 byte threshold, right? So it doesn't use heuristics or anything. So you have to be aware, maybe you're doing a test, you know, a simple test, and you're like, well, why is this, you know, taking so long? Or, you know, you're looking at it and there's the pause, but they're using PIO. So if you do like a simple 128 byte thing, you might not see the DMA routines. Well, you won't, fire and so forth. So that's a specific example, but you do need to know some of the characteristics of what's going on underneath to kind of understand how that got translated into the real world, okay, from those abstracted APIs. The other big thing, and we kind of touched on that already, is you need to know where to use sync versus async, okay? So I said network drivers, typically that are already driving off of callbacks where they're recycling SKBs and so forth. You already have that model where you're optimizing for throughput, so you can typically use asyncs there. You don't care exactly when it goes, but as long as it just completes and you do your housekeeping off of the callbacks, okay? But you're going to have some latency there, right? With the synchronous, okay, one of the nice things now, and which kernel did that come in?
Yeah.
That where it tries to do immediate and
yeah, early 4X.
Yeah. I was too lazy to go run Git and check it, but it was somewhere in there.
It's like 4.1 or something. It's really old.
Yeah. So, yeah, old unless you're on some crappy vendor kernel from.
It's stable. It must be old.
Yeah, exactly. So the point there is, if you're on a newer kernel or if you're stuck on an older one, there's some great optimizations in there where you want to have very low latency. It will try to execute in caller context, and you can avoid a context switch, right? You avoid the sleep and reduce latency. Now, here's an eye chart. I want everybody to see this, and probably somebody would take a patch to maybe get it in the docs itself. But I always found, I had to explain this to a couple people before. You will find this in include Linux SPI.h, but the SPI overview docs are a little bit more terse about this behavior, and this is very, very good, okay? One of the optimization things when you're working on protocol drivers is that you want to be very careful about the behavior of the chip select, because the back-end controller often will have a very long delay if your chip select is unasserted, and then you do another transfer, and it's got to reassert it, okay? And it can handle just having the chip select asserted the whole time. You can change some flags in the transfer to keep that asserted all the time. There's default case. And so you use CS change to do that. This is where you can go read the full explanation of that, okay? And also you can use it as a hint that if you're dispatching a lot of transfers, right, you can have a hint that the next transfer is going to the same device, and so it doesn't have to drop the chip select. That can save you, if you go look at it on your logic analyzer or scope, it can save you a lot of time, right, in between those. So when you're optimizing, you need to be aware of these things. All right, quick thing on tools, and then we're done. You want a logic analyzer? Go take a look at these things. SIGROC has a great comparison of everything and what it supports, and it's pretty comprehensive. The SPI loopback test module is a nice little tester if you want to look at your performance with something that's a canned test. And then the SPI subsystem statistics that came in a couple years ago or so. Really great stuff. You'll find them under your bus.chip select statistics. And what's great about those is when you're thinking about that SPI sync stuff, right? And did I actually, how many times am I actually sleeping, right? Or actually executing in the context of the caller? You start having visibility of that per device, right? by, you see how many messages you sent, transfers you sent, oh, how many times I did SPI sync immediate, right, which executed in my caller context versus how many times did I fall asleep, right? Timeouts, so forth. And then this is really awesome. There's histogram SysFS attributes now. So you have buckets of size of transfers, so you can actually look and see with a histogram what your data looks like. So that'll help you out a lot when you're optimizing. All right, last thing, future, slave support is coming. And it's useful in some limited use cases because we have the hard real-time nature of slave support where it's a full duplex bus and you're going to have to respond with something as soon as you get that first bit clocked in, right? And so a lot of cases you can't do, but you can do things with pre-existing responses, things that are just a one-way command to your Linux system. So Geert Uterhoven has a RFCV2 patch series. He's working on some bug fixes, and he's got a couple examples in that where he has basically when you register a slave, you get this sysclass slave device. You can, at runtime, bind a slave protocol driver into that slave controller. And he's got two example ones, one that does latest uptime, that it's got pre-existing cached, and it can respond back with a time packet, and another one where he can power off, reboot, halt the system, just one-way command. So that's coming. I think he's got a new version coming soon, real soon now. I put him on the spot. That's it.
So I think we do have time for a question. If people could be courteous to Matt, who's given us a great talk. Hopefully we can be still just for this one question if there is one. Go ahead.